Okay, so while I think Clausius-Clapeyron is very important, and delta G is equal to delta H minus T delta S is very important, and we're going to get into some Henry's law constants that I think are very important. Today's lecture may be the most important lecture you hear from me, and maybe even like the most important lecture you hear while you're here at UCI, okay? Because this, folks, is what is happening. It is happening. I hope to be able to provide you with enough information that you can make wise decisions, and when you discuss this, that you'll have some basis on which to argue one way or another, okay? So, I have no idea where I got this slide or when I gave this talk, but it has morphed over the years into to this thing. I think I gave this at UC Davis about 6 or 8 years ago. We had been on that ship, so more than likely that's what it was. So I was asked to give a talk. I talked to Eric Popman's class a couple weeks ago, Chem 1B, and then I talked to I'm not sure, it's like a freshman seminar class on this day, actually, January 13th. So I'd like you to, I'll read this to you, but global warming theory. There was something in the newspaper that morning, so here I am supposed to give a lecture at 1 o'clock or 2 o'clock that day, and this is what meets me in the local section of the newspaper. The article, UCI study challenges data on emissions, blah, 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 that prescribes destructive overhaul in the world's energy system to combat global warming. It is consistent with the ideology that global warming is caused by CO2 emissions and can be stopped. This ideology is not scientifically proven, but only speculation upon which an enormous amount of money has been spent. It is likely that enormous amounts of money will be spent on it in the future without impacting the environment, but it will impact our wallets. It is a nicely written article with misguided sources. Okay, so this is the thing that I wake up to, that I'm eating breakfast, and I got to read this kind of stuff. And it's important for you to understand that for someone like myself, who has had the good fortune of being involved in atmospheric sciences, atmospheric chemistry since the 70s, that I work a lot of hours, folks. It may not show from the lectures I give, but I am here almost every day. I think I went from December 28th until about a week ago, where I was here every day. I mean, Saturday, Sunday, New Year's Day, you name it. And unfortunately, I wasn't working on lectures, okay? I was working on research, stuff that I do with Josette, stuff that I do with Aaron, and a variety of other people. And it's not so bad now. I mean, my youngest child is 21. But this is sort of the work ethic that I've had my entire career. And so working 70, 80 hours a week and doing a lot of travel is not always the best thing for a family. And so I've made a lot of sacrifices. And so when I hear people say this kind of stuff, I bristle, because I am in a much better position to comment on this. And trust me, folks, if I didn't believe that what I was doing was actually important, I couldn't justify being away from my family. You know, I'd work 40 hours a week, and I would golf, or I would have a hobby, of which I have no hobbies. And so, yeah, I know, I'm really a one-dimensional person. And so the point is, folks, is that I am not alone in this, okay? All of my colleagues who are involved in this work like I work. And it's not that I don't feel rewarded from it and all that, I certainly do. But the point is that it's not easy to work for something like this if you're not convinced that you're making a difference, okay? So I'm very fortunate I've been able to feel that I've been making a difference. But I bristle when some knucklehead, you know, who thinks they know more than I do, or more than a climate scientist, because You know, they read a book or they watched some crazy TV show. So anyway, so you all should have at least heard the phrase climate change or global warming or greenhouse gas. Okay? Yes?
Did you write back to him?
You know, no. You know, because it's every month or every couple weeks, somebody writes in, somebody who has a degree in economics or a degree in who knows what, who thinks they really do know more about a topic. It would be like me writing in, you know, criticizing some person who's a history professor, you know, and saying, oh, you got the history wrong. You know, anyway, it's very irritating. My wife says, why do you even read that section of the newspaper? You know, 'cause all you do is get pissed off. But I don't write because, you know, it's just a time sink. So anyway. Okay, so why should we care? Okay, these are all things, folks. These are all things that can result from climate change. Sea level rising, we'll talk a lot about that today. Just a change in climate. Shifting ecosystems, stronger hurricanes, species die off, and ocean acidification. So let's right now think about this for a minute. When we say sea level rise, what is one reason why we would have sea level rise with climate change?
Melting of glaciers.
Melting of glaciers, he says. Okay, now, yes. Now, it's very important, folks. Are you asleep already? Jeez. I was going to ask you to help me here. It's okay. If Rafe had an ice cube in this, can I borrow this?
Yeah, go ahead.
Okay. If Rafe had an ice cube in here, and I drew the line, let's say that it was right here, is where the line was, where the water level was. There'd be a little bit of ice floating. If I let that melt, guess what? That line doesn't change. Okay? Thank you very much. That line doesn't change. So the ice, folks, that is in the north, there is no continent, there's no land in the north, okay, above Norway and all. So there's about this huge area where the North Polar ice cap is, okay? But there's no ground underneath it. It floats. So that whole thing, folks, if it melted completely, zero change in sea level. Okay? That's anything that is floating. Now glaciers, like this young lady said, are not floating. Glaciers are stuck somewhere. Okay? They are stuck in Greenland, or they're stuck in Chile, or they're stuck in the Andes, or different places like this. And it's just because the snow accumulated. And in fact, we have glaciers that are melting now that were the result of the last ice age, which was 10, 15,000 years ago, and then went back 100,000 years. So it is the ice, folks, that is on the land, okay? And that means Greenland, that means Antarctica, okay? 3%, folks, 3% of all the water in the entire world, all the oceans, is sitting on Antarctica. That's a lot. If that all melts, I think I heard that the sea level rises 180 feet. That's a lot of feet. Okay, there's no UCI if that happens. Okay? So sea level, we're going to talk a little bit more about that, is a huge thing, and I'll show you some slides and all about the sea level change. When I say change in climate, I remember when I was a student long ago, the projection when they talked about change in climate was that sort of the Southern California climate that we're so lucky to have here would move north. Okay? Would go to San Francisco, would go to Northern California instead of Southern California. And we would look more like Baja California. All right, that's what is expected, okay? Now, so lots of changes in terms of climate. You know, flowers blooming earlier. less snow. I mean, there was a big article in the newspaper this morning that talked about that these crazy weather patterns and stuff that we're getting right now are the result, to some extent, of climate change, certainly climate change. And what we're going to talk about, though, is the difference between climate change and anthropogenically induced climate change. That's the big thing that we're going to talk about today. Shifting ecosystems. All right. We've talked about combustion reactions. Remember, I would say you got methane, CH4, plus oxygen, a little bit of flame, and you end up with CO2 and water. How many remember that? Okay, that's a combustion reaction. Well, just about the opposite of that, not quite, but just about the opposite, is photosynthesis. Okay? You water a plant, it sucks in the CO2, and it makes, cellulose or complex carbohydrates or something like this. Okay? So it does just the opposite of combustion. All right? So plants suck up CO2. So today, folks, I'm going to talk a lot about spin. Okay? Because climate change is the most spun topic I've ever encountered. Okay? How many think they've got a good example of spin? How many? Okay, I'm not going to ask you to raise your hand, but I'm going to pose this question to you. How many of you don't really know what spin is? Okay, oh good, okay, raise your hand, sure. Okay, so spin, folks. Okay, so let me tell you a story. I'm going to take my jacket off and get comfortable here. Can you hold that for a second? Thank you. So, spin is where you tell a story and you tell the truth. Okay? But it's misleading. Thank you very much. So, I'm an old guy. Okay? I grew up during the Cold War. I mean, the 50s and 60s, when I remember in elementary school, we had air raid sirens that would go off, I don't know, once a week or something like this. I mean, there was the threat of nuclear war was huge, especially after '62 and the missile crisis in Cuba. So we had all these things we were supposed to do. We had points we're supposed to go to in case we were bombed, and they'd have a signal that would go, and you're on the playground and you're supposed to do some stuff. I mean, it was a very, very stressful time for kids. And the way that the Soviet Union was portrayed to us Americans, and once again, there was no internet. Okay, we had 3 channels of television, 6, 8, and 10. That was it. Okay, so we listened to radios and that type of thing. But if you only have 3 channels and no internet, it's a lot easier to sort of feed the masses with what you want and not to let them have any information about what is really happening. Okay, so I'm not sure things were as bad as they made it sound, but my 5th grade teacher introduced us kids, little 10-year-old kids, to spin. Okay, and here's the story he told us. He says that in this hypothetical situation, there was a race between an American running race, American and a Russian. Okay, the Russians were seen as like the worst of the Soviets. Okay, and the American got first. Okay, the Russian got second. In the Russian newspaper, the way it would be described is Russian runner gets second place, American runner gets second to last. You get it? 2 people run. That is absolutely true. But do you think that's a little misleading? Would you raise your hand if you think that's a little bit misleading? Once again, absolutely true, but it's spun. The story is told in a way that makes one side look better than it is, okay? So what I will tell you about today, folks, is several things. How things are spun to cast doubt that if you really don't know the theory of climate change or global warming, that things can be said, data can be presented in a way that really are convincing and actually is very accurate and yet totally misleading. Okay? So that's spin, all right? And so we'll talk about spin. Anyway, one of the things that is commented about is that this increasing CO2, carbon dioxide, which is given off, once again, burn something, coal is just carbon. Carbon plus heat and oxygen, CO2 and water, okay? Or just CO. So the carbon dioxide is what we are worried about. And so the people who are opponents of this and who like to make it sound like those people like myself are just nutcases, say, look, CO2 is a fertilizer, okay? Plants use CO2 to make, cellulose and stuff. Absolutely right. That is absolutely true, okay? Problem is this, is that when I say shifting ecosystems, not only will you have warmer temperatures, creeping up further and further north. You got to remember, folks, during the last ice age, folks, there was no Alaska and there was no Canada. No Canada at all. We had glaciers all the way into Colorado. So the whole North America was completely covered in ice. Okay? So we're talking about, the temperature here in Southern California was radically different than it was, okay? So clearly back then, we had pine trees growing down here as opposed to grass, okay? So shifting ecosystems, but think about it. Let's say you have 5 kinds of plants. And by doubling CO2, this plant grows 20% faster. All plants grow faster with more CO2. Okay? All plants grow faster. Let's say this plant here grows 20% faster. This plant right here grows 30% faster. This plant right here goes 100% faster. And let's say in today's world, these 3 plants coexist and sort of inhabit a similar area. Okay? And all of a sudden, they all benefit. So that's the spin. Well, all plants benefit by having more CO2. True. But let's say this plant, which grows twice as fast now, ends up growing bigger and starts blocking out the sun that this plant used to get. So even though this plant could grow faster, now it's got less sun. And this plant might die off. So we've got species die off. Okay? So it looks like you would benefit, and in fact, you don't benefit. So that's a little bit of a spin thing. Stronger hurricanes, I'll just say that that's the case. And what's interesting is that these people, like the person who wrote that article, people who say, how can you think that CO2, it's unproven that it's going to cause global warming and so on and so forth. CO2 is increasing. Just by increasing CO2, we are acidifying the oceans. The oceans are more acidic now than they were 50 years ago. So even if you don't buy into the fact that CO2 is causing the temperature of the Earth to increase, this is happening. I mean, there's measurements. And when this happens, all kinds of crazy things happen. Coral goes, anyway. So the point is that the whole CO2 thing, it causes lots of problems, okay? So, I want you to, because you folks, not just you folks, me also, tend not to think a lot, okay? Have you ever wondered, how many of you have ever wondered what happens to the sun's radiation that hits the Earth? Okay, so here we are, this little ball 93 million miles away from this huge source of energy, and it's constantly hitting the Earth. Why is the Earth not warming up? Why do we, and I don't mean it gets warmer during the daytime and colder at night, I mean on the whole, why does the Earth not just keep warming up? This thing is, the outside of this sun is 6,000 degrees. We are 300. Yes?
We have bodies of water to sort of cool that.
Okay, well, so she says we got lots of water here, yes. But eventually, after a billion years, yes?
Is it ozone that's bounced up?
No. Okay, he's asking about the ozone layer. No, yes? That's right, the Earth is giving off radiation. Okay? So, energy is given off by the Earth. The maximum radiation, so this the outside of it is 6,000 degrees. That's where we see the radiation, and the maximum radiation given off of a body that's at 6,000 degrees is in the visible. Okay? This is a spectrum, or a breakdown. Okay? So this is the solar radiation. This is what we call the black body curve. Something that's completely black. Something completely black that is just warm. How many of you have an electric stove? Or have ever seen like a toaster oven that's like electric but not gas? You ever notice that little filament gets sort of like orange? It starts off it's not shiny, it just starts off as looks like a piece of charcoal or something. And then you turn on the oven or the burner or whatever, and all of a sudden you notice it gets a little bit orangish. Or, I don't even know if you guys have cigarette lighters anymore, but when I was a kid we did. You plugged them in, my dad smoked cigars, you push that thing in there and all of a sudden it pops out and you look at it, it's got sort of this little glow plug, kind of an orangish looking thing. It was like 2,000 degrees, hotter than the son of a gun, okay? Well, anything that has, as we call a black body radiation, means that something with no reflection or anything is going to give off energy at certain wavelengths depending on its temperature. And the sun, its black body curve is this right here, okay? It's right in the visible, okay? Visible radiation is right here. The Earth, in order for it not to just keep heating up and heating up and heating up, it has to give off as much radiation as it receives, right? That's called thermal equilibrium. If I end up with 100 joules of energy, I will heat up unless I get rid of 100 joules of energy, okay? That's how it works. So the Earth at a temperature of about 300 Kelvin instead of 6,000 has a black body curve right here, all right? And this is a little tiny curve. It's 100,000 times smaller than this, actually. But this is the actual black body curve of the Earth. And so, yes, as the guy up there said, the Earth gives off radiation. The sun gives it off in the visible, we give it off here. So if you're in outer space, you had some like infrared binoculars, you're some spy guy, and you look at the dark side of the Earth, guess what? It glows. It's like this fiery ball. It is giving off a tremendous amount of radiation. In fact, it's giving off as much as the sun gives us on a daily basis. But not everything that the Earth gives off. I mean, if where I'm standing right here is the Earth's surface, and up there is outer space, then if the radiation that is leaving down here at my feet, if it goes all the way up and out, then we get rid of it. But if it comes up and is absorbed by something, then it's not gotten rid of, okay? So, what makes a gas a greenhouse? This is on the exam, okay? Write this down. It will be a multiple choice question, and it's going to be, which one of these is not a greenhouse gas? Or which one of them is? I'm not sure. And I will tell you how to determine whether something is or is not a greenhouse gas. Carbon dioxide, water, and ozone. Those are the three natural and most important greenhouse gases. Okay? I'll show you a figure in a second that's quite impressive. Those three are natural. They've been around for 1 billion years, and while they may change in concentration, these are the ones that really contribute the most to our Earth's temperature. So, in order to be a greenhouse gas, you have to absorb infrared radiation. You must have molecular vibrations. Okay? That means, folks, that something like argon, which it doesn't have anything attached to it, just AR, it can't vibrate, okay? And so anything that's just a monatomic cannot be a greenhouse gas. You have to have some different kinds of stretches. It's beyond this class. But homonuclear diatomic molecules only have symmetric vibrations, and you need some non-symmetric. So that means that N2 and O2 are not greenhouse gases. So what we're mainly breathing in this room right now, which is oxygen, nitrogen, and argon, none of those are greenhouse gases. And it kind of makes sense. I mean, if they were, then, you know, making up 99% of the atmosphere, we wouldn't have to worry about much else, okay? But these are not. So something like argon, which is just a mono atomic, and then these guys are not greenhouse gases. Generally speaking, folks, things with 3 or more atoms can be greenhouse gases. They're not always greenhouse gases, but they can be. So CO2, water vapor, these are the natural greenhouse gases. You will be asked a question something like that. These folks are gases, CFCs, chlorofluorocarbons. That's like a carbon, 2 chlorines, 2 fluorines. It's got some anti-symmetric stretching. So CFCs are very good greenhouse gases, very strong. SF6 is totally anthropogenic. That means man-made. That means that this, if we go back and look at ice cores from 100 years ago, there's no CFCs, there's no SF6. None, okay? These are completely industrially manufactured and released. Now these folks, methane and N2O, are in the natural atmosphere, okay? But methane, this is what I did my thesis on back in the 70s. Methane is, right now is about 3 times higher in concentration than it had been 100 years ago. But it was natural, and N2O is a natural one. But now we're adding fertilizers to fields and stuff, and so we're making more N2O. But these are all greenhouse gases, okay? These 3 are the main ones. So you're going to be asked on the exam, okay? And there'll be CO2, water, ozone, methane, and something. Oxygen, argon. Something that is not a greenhouse gas. Okay, or I'll be really a turkey, and I'll say oxygen, nitrogen, argon, neon, and methane. Which one is a greenhouse gas? And it'll be methane. Okay, don't forget, three atoms is a bit of a clue. So this is a hand-colored figure from Cherry Rowland. He used to love to color things. So he had these black body curves. So this is the black body curve at sort of this wavelengths of radiation here. Black body curve for something that's at 200 K, and then 220 K, and 240 K, and 260 K, and 280 K, and 300 K, and 320 K. Okay, so this shows you what the spectrum looks like for something at that temperature. And this is actually a satellite flying over the Sahara, okay, at about noontime. Sahara, and I forget what time of year it was. It doesn't really matter since it's pretty much in the tropics. But very hot, okay. This curve right here is the 320K curve. And so if we look at this big band in this area, which is water vapor and a little bit of methane, this is really more water. This is the water vapor band. This is the ozone band, and this is the CO2 band. So looking at Earth from up in outer space, this big chunk, okay, of radiation, it should have gone all the way up to here. This top curve is the one that should be if there was no atmosphere. That is what we should have seen, okay? And instead, we see big pieces eaten out. Here's a huge absorption band, okay, that CO2 has. Big ozone band right there, and so on. But you integrate this, and what you can see is that CO2 and water vapor are the main greenhouse gases, okay? But ozone is clearly important. This, folks, is what we call the window. Okay? What this window is it's an area where the Earth is pretty effective in whatever's being given off down below getting out. Okay? So if you happen to, if the radiation happens to be at 800 wave numbers or 900, look at that. Shoot. There's very little absorption there. Okay? So this makes it all the way out. So this is the window. So if you put something into the atmosphere that absorbs it in the window, it's extremely effective because there's a lot of that radiation available. Okay? If you put something in it that absorbs at 700 wave numbers, look at this. There's like none of it left. Okay? CO2 is completely dominating that band right there. But you move over here, and there's a tremendous amount. I say this is the window. And so the problem is that CFCs absorb right in here. So one chlorofluorocarbon molecule is as effective as about, in removing outgoing radiation, as like 20,000 CO2s. It's huge. Okay? So this, once again, is a window where a lot of these man-made gases go. Now, folks, CO2, ozone, water vapor, natural, okay? We're adding a little bit of this and a little bit of this, but this is the reason why we are warmer than we could be. So here's a little cartoon. Now, I've phrased this question on an exam different ways, and I'm not sure. Let's go with Celsius, okay, or Kelvin. Let's go with Celsius, because my brain's not thinking today. Once we got satellites that could actually get up and see how much radiation was coming from the sun, then we could estimate what the temperature of the Earth would be with and without an atmosphere. Okay? So without an atmosphere, like the moon, okay, does anybody want to guess what the average temperature of the Earth would be without an atmosphere? About 0 degrees Celsius. 0 degrees Celsius. That's not right. Sorry. Get rid of that. See, it's 0 degrees Fahrenheit is what it is. Okay, 0 degrees Fahrenheit. Does anybody want to guess what the temperature actually is because of the atmosphere? 60 degrees Fahrenheit. Huge difference. 60 degrees Fahrenheit is the difference between what the average temperature of the Earth would be without an atmosphere versus what we live in. Okay? 0 degrees Fahrenheit, folks, is way below freezing. Okay? So basically, the Earth would be habitable in the equatorial regions, and that's it. So that's because we have an atmosphere. Okay? We have an atmosphere. CO2, water vapor, and ozone are the reasons that we are 60 degrees Fahrenheit warmer, and that corresponds to about 33 degrees Celsius. Okay? 33 degrees Celsius is or 60 degrees Fahrenheit, whichever, that's the difference that an atmosphere makes. Okay? So, that is what three gases, water vapor, ozone, and CO2. Okay? That's what those gases do. They increase our average temperature of the Earth by 60 degrees Fahrenheit. Okay? So now, folks, here is what I'm going to tell you. If you get into a discussion with somebody and they say they do not believe in greenhouse gases, walk away. They are stupid and fools, okay? And if they're trying to argue that there's no such thing as climate change and they don't believe in greenhouse gases, once again, you're talking to a rock. So just walk away. Now, if they say, look, I understand that the Earth is warmer by 60 degrees Fahrenheit because of the greenhouse gases, I just don't believe that you can change that by adding more greenhouse gases. Then at least they understand how this works, okay? But the folks, the point is that these three gases have increased the Earth's temperature, or the reason why we're 60 degrees warmer, okay? So my question to you is if, and that's not debatable, I mean that is a fact, okay? This isn't some theory, okay? We can go to outer space and look, and we can see what the temperature is there and how much radiation is hitting here, and it's about 60 degrees difference because of our atmosphere. So, knowing that, the question is that if we now add more of those three gases, let's say, or in the case of just CO2, if we add more CO2, does it seem completely implausible that by adding 10% more CO2, that we might see a small temperature rise because of that additional CO2 that we've added? I'm not asking you to believe that, okay, you know, that some theory. I mean, the CO2, you saw that figure, okay? Look at this. Look at what CO2 does. That's the absorption from CO2. So I'm not telling you, okay, let's say we put some gas that absorbs in here. Okay, and right now it's there, and I'm talking about increasing it by a factor of a zillion, so now it's down there. That's different. This, folks, is CO2. That's what 350 or so parts per million of CO2 will do. So all I'm saying is it a huge leap of faith that if this is what 350 looks like, that 450 might come down a tiny bit further and look a little bit like this. Okay, that is what I'm trying to convince you that could happen or is happening. And in this case, how about ozone? Ozone's not nearly as much absorbed. If you add more ozone, more methane, some of these other gases that absorb in here are very, very important. Okay, so that's what I'm trying to get. Any questions? Ask me a question. I don't have to finish this. Any questions? Okay. Well, ask a question if you got one, okay? Okay, so here we are, 33 degrees warmer Celsius because of our atmosphere. So, this is something you do not need to know. It's just I want you to have this information. We're going back to 1750 because that's about the time we started using coal and that type of thing on any kind of a level. So that before that, mankind wasn't really doing too much damage to the atmosphere on a global scale. And so what we have people here on this campus in Earth System Science, I don't do it, who have what we call climate models. And they put in to their models different gases and concentrations of gases and lifetimes of gases, how they're removed, how they're added. And in terms of radiative forcing, the amount of energy of absorption by these gases, CO2, methane, N2O, and halocarbons, since 1750, so for the last 250 years, we think is about 2.5 watts per square meter. Okay? That is what we think. So this is by adding a whole bunch of CO2, this is how much of an absorption we are attributing to that. Come over here, the fact that stratospheric ozone is decreased. Anything below the line and that's in blue means that it's cooling. Anything in red means it's warming. So this is how much warming in terms of watts per meter square from gases. And that little error bar there, folks, tells you that that's the confidence that we have in that. We think that we know to within that level, about a half of a watt per meter square, that number is a good number, that it's between 2 and 3. This one here says that, well, you know, we have an error bar on here, and this looks like it's about 1/4 of a degree, but our error bar is about 1/4. And then tropospheric ozone. I go to China and I go to Saudi Arabia and other countries because, and Los Angeles, because we tend in our pollution from cars and biomass burning and stuff to be generating more ozone down here. Not the good ozone, but the bad ozone. And that's what this is. And then you got sulfates, which are an aerosol that reflect sunlight. So you reflect it before it even gets to the earth. And so that's a cooling. Black carbon, we're not sure. Biomass burning, a little bit of a negative here. Mineral dust, you can see we don't know. Mineral dust, we're not sure what's going to happen with mineral dust. And look at the aerosol indirect effect. It's either 0 or it's -2. So if this aerosol indirect effect is here, then we pretty much have no climate change from the greenhouse effect. Okay, because look how this is like a -2, and if you were to add all the negatives up and all the positives up, it would be very close to 0. But this also could be 0. So for your guess is as good as mine as to where are we? Okay, but this is what my group does. We measure these gases. All right, and I can tell you those gases are increasing. This is just coal use. Okay, coal, oil, that kind of stuff, folks, is stuff that, you know, forests and swamps and I don't know what, dinosaurs that fell into something and then slowly went down, and with plate tectonics and stuff, and now it's 2 miles down and it's kind of warm down there and it's had all this pressure, and you end up making coal and oil. So for millions of years, that carbon had been down in the ground. Okay, and now what we're doing is we're digging it out and we're burning it, and that's what's happening. So this is CO2. So the blue was coal. So 150 years ago, all we had was coal. We didn't start getting. Okay, here's the total. We didn't start using any kind of gas or oil until about 100 years ago. But for the most part, the black one is the total. And you can see, this is a log scale, folks, okay? So this number here is like 10, 20, 30, 40, 50. About 50 times 10 to the 9th kilograms of carbon per year. And now in 2000, we're at about 8,000. Okay, so we've gone from 50 to 8,000. So this is how much carbon we've been putting into the atmosphere. And there's different ways to look at it, okay? I do a lot in China, and I am irritated by the American press anyway for slamming the Chinese for their use of carbon and CO2 emissions and all. This is the Atlas of Pollution. Okay, so here's the United States. This is in CO2. We're down 7%. Look at, most of these have arrows that are heading down, okay? And the size of the sphere is how much we actually are giving off now. So clearly, the biggest one is China, the next biggest one is the US, and then India, and then Russia, and so on. I can't read these. So these I show only because it shows the percentage increase, okay, or decrease. The good news is that a lot of places are going down. Problem, folks, is that places like the United States and some places in Europe want to tell China that you cannot do what you're doing, okay? That is so unfair. Because here's the per capita, okay? Who's the #1 per capita polluter of CO2 in the world? Good old us, okay? Europe, Asia, look at that. Those guys are, you know, they're way behind us, okay? And if you want to look at how much we've ever put into the atmosphere, look at this. So here we are, we put in 300,000. Poor Chinese are here in #3, okay? They're gaining all the time, okay? But you got to remember, there's like 3 or 4 times more of them than there is us. So here we are saying, don't do it. We did it. We benefited. We got this wonderful society. We've got, you know, all of our perks. We got our cars, our nice streets, and, you know, our street lights and all that. And we're saying to them, you can't do it. That's bullshit. Okay? I'm sorry. I mean, I'm not happy that they are giving off as much as they're giving off, but you know what? We did it. How can we look at anybody and say, you know, we can always say, you know, well, you shouldn't do it, okay? And actually, they're not doing nearly as much. anyway, I just get irritated because I've had students say, well, you know, why are we doing anything? Those damn Chinese are just going to screw it up for everybody. That is absolutely true. I had like a heckler once. You know, I was shocked that a student would talk to me, an esteemed professor, with that tone, you know. Anyway, I think it's, so I show this now ever since I gave that lecture because I think it's totally ridiculous that we would use as an excuse, well, why should we cut back on our CO2, you know, when the Chinese are putting out all this stuff? Okay, so anyway, that's enough of my racist rant. Okay. Here's what's happening to CO2, okay? Look at this. These are real data. This isn't some theory. These are Dave Keeling's data from 1957 at Mauna Loa, and look at this. And every year it goes up in the wintertime, and then the plants and the plankton suck it down. Look at that. Isn't that beautiful? Every year you see it. But look at that change. Okay? It used to be going up at this rate, and now it's actually steeper here, and that's just because we're kicking out more. This is the CO2 that we're seeing, folks. So this only goes to 1957, and then it was 315. Now we're actually up to, I mean, this only goes to, I'm not sure, but it's not into 2010. We actually went over 400. At least in the Northern Hemisphere not long ago, on average. So the point is, folks, is we're seeing a huge change here. Just in my lifetime, that's happened, because I was born here. Okay? So just in my lifetime, this is what's happened. We've increased CO2 by about, you know, 80, 70 parts per million on a background of 250, 270. It's a significant amount. Should we expect some change, or is it? I say yes. Don't get me started. Okay. Yes?
Is there anything like humans can do to reduce that?
Okay, we're going to get a little bit to that. Yes, yes. So, we have ice cores. We have, it's like a history book. Okay? Ice cores where the snow goes and it lands and it traps stuff and eventually it becomes a bubble in ice. Okay? We can go down 1 million years in some cases. All right? So I don't do that, but there's a guy in Earth System Science over here, Eric Saltzman, who does do that. So this is 400,000 years ago. We can dig down, we can date it, and we can tell what the temperature was. And this is the temperature, believe it or not, you can tell the temperature from the ice. Not the temperature of the ice, but the isotopic ratios of oxygen in the ice. So this is the temperature, and look at methane. Every time there's a burst, methane is bigger. Okay, and look at CO2 is bigger. It's not so much that that the methane CO2 are driving this. Something happens to trigger this, but as soon as it gets triggered, then the methane and the CO2 are going on. Now look, these are the temperatures, folks, and this is a little misleading because this is 400,000 years here, and now this is only 100 years. So if this weren't expanded, it would be shooting up like really a lot. Right here, okay? So temperature is going up. It's warmer than it's been in the last 400,000 years, almost. Maybe that looks awfully big there. But look at what's happened to methane and CO2. Methane, blah, 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 between 400 and 800. And now here we are at 17, now it's at 1780. Okay, and CO2, you know, the biggest it had been was about 300, and now in 2004 is 277. As I said, now it's up to almost 400. Huge. In 400,000 years, we've never seen it. Okay? Now, for those of you who say, well, who cares? The temperature of the Earth has actually been warmer than this in the past. Absolutely. Absolutely, folks. Okay? But what you can't see is even though this looks like a very rapid change, and we call this abrupt climate change, guess what? It happens slower than what's happening now. Okay, we're doing such a perturbation on our atmosphere that we're climbing at a much faster rate than ever before. And so that's the problem is that we're not letting things equilibrate. This is perfect. Equilibrium is what we're supposed to be talking about today. Okay, you know, something, you know, where the temperature changes by a degree over a couple thousand years allows the plants and everything to sort of slowly move. You know, they move a foot a year or 2 feet a year. That's easy to do. But to move 100 feet a year is not so easy. Anyway, so this is good stuff. So what we do, folks, is we model this. And what that means is we have our models, which are climate models. We put in the data from the slide before, the data of the temperature, the data of the CO2, the data of the methane and all, and then we plot it. So here's the observations are in red, and the calculated temperatures are in blue. Okay? So it's all retrospectively. We already know the answer. Okay? But if you look at this, I think you would admit that the calculated temperatures hit pretty well. Would you say that? I mean, they don't match every little bit here, but for the most part, look, it dips here, goes up here, comes down here, goes up here, goes up here, and goes there. So the models are pretty good at predicting. Okay? And then what you do is you say, okay, now I'm going to start here and predict that way. I'm going to predict into the future to see what is going to happen. Okay? Because who cares if we can predict what happened in the past? Okay? That's how these models are tweaked. Okay? And then you run them forward. So here's a good example. These are data that just go back 150 years. So the model is gray, the observed is red. And if we look at this, you know, they don't agree all that well here, but they certainly don't agree here. All right? This is the observed. This is the actual temperature, average temperature of the Earth, okay, right here, and we're missing it completely, okay? That is only with natural forcing. It's solar and volcanoes. This one, also, we've added the gases and aerosols. So look at that. I say that's pretty good, okay? So without the gases, we miss, and with the gases, we hit pretty well. So to me, folks, this says, okay, the modelers are doing a pretty good job. If the modelers say that then under these conditions, if CO2 goes from 400 today to 600, and if methane goes from here to here, those are all ifs. Could change in a heartbeat, okay? But if these things happen, then we can expect a certain temperature here. And that's, folks, are the predictions that we see. Okay, the predictions are just from these models. They use UC Irvine data, but they are models that, they're the best models we have. Are they perfect? Heck no. Okay? If they say that we can expect a 2-degree change, it's not 2.00 degrees. It's going to be 2 plus or minus, 1 or 2 plus or minus a half. Okay? Okay, so here's just a little bit of Greenland. This is, once again, what's happened in Greenland just in the last 20 years. A lot of melting all around the edges. Now that, folks, is water that was not in the ocean, that is now in the ocean. So sea level will rise because of that. Bless you. So this is the North Polar. So look at the difference. This is 1979 at the same time of year in 2003. This is polar ice. Which do you think has more ice in it? This one or this one? I think it's this one. Certainly it's a lot thicker here. Okay. Now, I already told you, it doesn't matter if this melts. It's floating. So it doesn't matter in terms of adding any sea level rise. The problem, folks, is reflection. Okay? What I didn't tell you is that about 30% of the of the sun's radiation that hits Earth just gets reflected. Okay? Now, what's going to reflect something that's white or something that's dark? Something that is white. This reflects very, very well. The blue absorbs. So the problem, folks, is not the melting. The problem is that as this melts, you have a bigger area that is dark, that absorbs the radiation, heats things up, and then melts this even more. Okay, so it's this positive feedback. Let me show you some photos that, this is just a plot of sea ice. Look at how it's just decreasing with time. Okay? It's quite scary. Okay? Look at this. This is a photo taken in 2005. This is an ice sheet in Antarctica. I took that picture. Here's the plane. It had wings as big as this room. Okay? Almost. And so this is a huge ice sheet. Look at this. What's going to happen right here? Plop. Okay? This is going to fall right in the ocean. Now look at the difference between a light hitting right here and a light hitting right there. This hits this white and just You know, I mean, trust me, I had to wear different kind of goggles, okay, because this is so bright and reflective. When you look out of the ocean, not a problem at all. Huge reflection here, almost no reflection here. So as this just gets chewed up and goes this way, then there's more of this very, very dark ocean that can absorb the sun's light instead of reflecting it, and it has this positive feedback. The more it breaks off, the more area, the warmer it gets, the more it breaks off. Okay? And I think I got one more just to show you just how far that ice sheet goes. So, in class, folks, I showed you a curve. It was the density of water versus temperature. Do we remember that? The density of water versus temperature. And I'm going to walk up here and I'm going to point to somebody and I'm going to ask, what is the temperature at which the density of water is at its greatest? You know that answer? 4 degrees, he says. Yes, 4 degrees. Anything on the colder side, the density decreases. Anything on the warmer side, the density decreases. So let me ask you this. We've got an ocean that is warmer, at least on the top, warmer than 4 degrees. Okay? If we warm that up a little bit more, what happens to the density? It's going to decrease. Anything moving warmer, if you're already warmer than 4 degrees, and you get warmer, the density decreases even more. Okay? So guess what? We have water in the ocean that's going to swell just because it warmed up a bit. So even with no melting at all of anything, if the temperature of the earth or the world or whatever increases by 1 degree, sea level is going to rise by, I don't know, half a meter or so. Just from that. That doesn't count anything that's running off the glaciers in Greenland or anything from Antarctica. Look at this in sea level. So 150 years, 120 years, it's gone from here to there. 20 centimeters. It's this much. Okay, you may not think that's a lot, but there are islands now that are no longer islands because of that change. Okay? And that's how much we've done in this period of time. I've said that if we warm by 1 degree, it's going to go this much. Okay? Huge, huge problems. Okay? So here's sea level, actual data. Okay? Now, I don't understand this. Maybe you young, smart people can help me out with this, but I just don't get it. I believe it, but I don't get it. This is the trend of sea level, so between 1993 and 2008, so a 15-year period. 0 is sort of this color right there, which I think is like that color. Okay, like these right here. 0. It hasn't changed a bit. Okay, per year. Here, we have an area that is going down in sea. How can that? I don't get it. It's not a hypothetical question, folks. I am perplexed. How can the sea level go up in one place and down in another? I thought it was like one big connected system. Is this a little bit bothersome to you? I mean, if I told you that off of Newport Beach, sea level had risen a foot, and in Catalina it was down a foot, that would make no sense. Anyway. But it's happening. This is what's happening. So look at this. Huge red spots. That's like 7 or 8 millimeters, this much per year in the 15 years. So you see red spots, and look at, there's some blue right there. But you tell me. This color right here, that color, means it hasn't changed. If on an exam I said, looking at this figure, would you say that on average, sea level in 15 years has increased or decreased? What would you say? How many say decrease? I mean, to me it looks like there's more green and red than there is blue. Okay? So overall, it's a decrease. But look what happened off the coast of California. So guess what was in the newspaper? NASA proves that sea level is not rising. Yes, absolutely. Somebody from Newport Beach wrote that. And you know what? It's true. I mean, it is true that off of Newport Beach, sea level did not rise in the last 15 years. So that is spin, because you're looking at a small little area. But for the most part, it's changed a lot. Okay? So we have to worry about sea level. Okay, these are just northern hemisphere temperatures. I think I'm going to skip that right now. Myths or spin. Okay, you're going to hear people who are on the other side say, well, look, the temperature really isn't doing that. It's because these people who do climate work are so stupid, like Don Blake, that they would put like a thermometer in the middle of a city where you got people and you got cement and it's just warming up. Or you put it in an airport, okay, where you got cement and runways. That there is no sea level rise, I just showed you that in some cases that's true, but generally speaking that's false. No temperature rise, okay? And once again, if you go to the far north, the tundra is melting. I mean, they're seeing huge temperature changes there. ClimateGate, which was where somebody broke into the University of East Anglia, somebody's computer, and stole a bunch of emails. And these emails were between different climate scientists. And the thing is that the climate scientists were arguing about data and what this meant and so on and so forth, and some were arguing that it should be left out because it was confusing or whatever. Nobody in those emails said that the temperature was not increasing. Okay, it was the extent of the increase. One person said, well, I think it's only going up 1 degree in 100 years, and the other said it's going up 2. Nobody said it's going down, and yet people like to grab onto this ClimateGate and say, oh, this just proves that it's all bogus. Okay, trust me, it's not. And you can use small time increments to spin data. What do I mean by that? Okay. I think I came up with a pretty good analogy. I think. So, I call this like an infinity pool, okay? And let's just play a game right now. Let's just say that I need to put 100 gallons a day into this pool to keep it just at the top because of evaporation. That I evaporate 100 gallons a day, and so if I put 100 gallons a day in, I can keep it just at the top with nothing going over. So I put in 100 gallons a day, all sort of spaced so that it's not all in one shot. And I put in 100 gallons a day, and I got no overflow. Okay, let me ask you a question. If I put in 99 gallons a day, am I going to have overflow? What if I put in 101? Yes. 101, all of a sudden, I'll have 1 gallon going over. If I put in 102, I have 2 gallons. So in one of the articles written in the newspaper in the local section, they said this whole CO2 thing is bogus. There's no way that humankind emissions are causing this CO2 increase because it's really only a few percent of the total amount of CO2 that's put into the atmosphere every year. It's true. It's like 3%. Okay? But guess what? It's because the other 97, we were in equilibrium. Okay? We were in equilibrium. And now we're adding 3% more, and now we got 3 gallons running off of this thing. So you can't make an argument. You can't say, well, look, it's only 3%. It's trivial. It's not trivial. Okay, well, don't get me started on this guy. This Fred Singer has made a career out of being on the other side of the fence from Don Blake and Sherry Rowland. I mean, he'll say anything for price. I mean, he was the one who denied that secondhand smoke was a problem for people. And of course, he was paid for by the tobacco industry. And he says, when he was asked by this, he says, it doesn't make a difference where the money came from. Right? Okay, then I got this off. This, I don't know, this just pisses me off. So look at this. The same group that says this. Global warming skeptics have proven to be, have been proved to be correct, which the below material supports. Okay? And basically all the stuff that Jim Hansen, Al Gore, and the IPCC, which I helped write, by the way, was just bogus. So here's the data that they say indicates that NASA and everybody else, that the skeptics are right. Okay? These are data, real data. Okay? I'm not sure what a hadcrut, whether hadcrut's a person or it's a statistical package. I honestly don't know. But this is CO2 emissions. This is temperature, okay, since 1996. You can see it went up and now it's down. And so the point is that we are cooler now than we were in 1996. And so this proves that there is no temperature change, okay? This is a 10-year hadcrut trend. Now I have no idea, same data, same exact data. When they then go to a 5, it looks like this, same data. So it's some sort of a weird statistical package. The point still is that the temperature in 1996 is warmer than it is in 2011. And I think all of us would have to agree with that, wouldn't we? I would. How many agree that from these data that the temperature in 1996, which is at a little above a 2.0 here, is greater than that point right there, which is at 0.0? Sure. Absolutely. But folks, this is spin. This is spin. Why? Look at where they got it from. They chose that point right there. Okay? So look at the trend. Boom, 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 boom. Okay? What they did then was they took this 1996, the highest one, okay, and they went from there to there. Okay? Real data. You can sort of see those little blips that were in that thing that I couldn't understand, okay? And now we're now back up to sort of in this range over here, okay? So we just had a super hot year. So they went from that. Look at this. Wouldn't you say the trend has pretty much been like that? Okay? You have an outlier like that. This is how they spin it. And they show data for, 15 years, and it looks like it's real, and it is real. Okay? But it's real wrong. Okay, so this of course really gets me going. Look at this. Ozone, stratospheric ozone, was the 1980s anthropogenic global warming. So this person is still saying that the whole ozone thing was bullshit. I can't say that word on being filmed, but I did it. Beware the scam of carbon trading. Anyway, this person, look, you replaced it with a less efficient and more expensive alternative. Ain't that just like the left? Shame. Golly. Okay, so the young lady asked me, what do you do? Okay. You try and, every little bit helps. You try and drive less, you take the bus, you don't only get, we got 5 minutes. Search the internet to look. Okay, you folks have the internet to look at, okay? Talk to each other, ask professors, be educated on this. And if some clown is sitting next to you on an airplane and is talking about how this whole global warming thing is a bunch of bunk, get in their face. Hold on, I think I got something to show you. Oh yeah, I think I've already shown you this, didn't I? Okay, okay, now so just so you know, Sherry Rowland is not the only one to get the Nobel Prize. Okay? I got it. Yeah, huh? That shut you up. So, as I said, I was one of the authors of the IPCC report, which was awarded the Nobel Prize in 2007. Al Gore got half of it. It was the Peace Prize. And then there were 2,000 of us, so it hardly counts, who actually received the Nobel Prize for our work on the 2007 IPCC report. And I think, spin, spin, okay, we're done. All right.